what we're going to do now is we're going to use the state transition equations that we had learned before and actually apply them with a couple real problems so we can sort of get an intuition of what's happening. So for the first transition matrix, we can use the following probabilities. And if you remember, we can sort of quickly draw what the diagram looks like. We have states 1, 2, and 3. A self loop with 1/3 for each of the states. And then we have 2/3 going to the neighbor. Okay. And so my claim was, if we want to know the probability distribution at some time step n, that's just given by p to the n transpose times whatever our probability distribution is at the starting point. Okay. So we can test this out just with something easy. First, we'll show that we'll calculate what u of 1 is based on having u0 equal to 1, 0, 0. And so we actually kind of knew what this answer was because we can just look at this first column. And we know, if we're in state 1, then with 1/3 probability we stay in state 1, and with 2/3 probability we go to state 2. And so the quick answer, without having to do anything super complicated or actually multiplying the matrix, we don't even need to do that. We could just say right off the bat, well, our distribution is 1/3, 2/3, 0. So what does this mean? That at time step 1, the probability of being at state 1 is 1/3. Okay. Now for this guy here, we have at time step 1 the probability of being at state 2 is 2/3. Okay. But just to prove to you that this actually works, which we kind of already did, but we'll just do it again, I'm going to show this in Octave. So I highly suggest everybody download Octave if you don't have like a graphing calculator that you know how to do matrices on. Alternatively, you can also use MATLAB. Octave is just the open source free version of MATLAB. Okay, so let's open up. I have Octave here. I downloaded it. And it's pretty easy to enter in your matrices. You type in the name of the matrix or the variable. And then what we're going to do is we're going to fill in a matrix between two brackets. And before I move forward, let me make the font bigger so you guys can actually read this stuff. Apply. Okay. Okay, there we go. Okay. So we want to fill out this matrix, and the way you fill out the matrix in MATLAB is you go one row at a time, and every time you hit a new row, you enter a semicolon. Okay, so this P matrix was 1/3, 2/3, 0. Right, so I have spaces between these numbers. If you'd like, you can do a comma to be clear. For the next row, I indicate that with a semicolon. We have 0, 1/3, 2/3, semicolon. So now I can begin the last row. We have 2/3, 0, 1/3. Okay. So if I press return, it's going to show me what P is equal to. And sure enough, that's what we wanted. All right. So now I'm going to define this variable u0. u0 is going to be our distribution of where we are at the initial time step. So I'm going to say we're going to start off at 1, 0, 0. Okay. Now, what we had done here is, let me close all this stuff or make it small. We had said, well, let's go ahead and calculate where we think we're going to be in the next time step. And I said we could do that by just taking P transpose and multiplying it by the initial state representation. Okay, so let's do that. So in order to take a transpose in MATLAB, we use this prime. Okay, so you can see when we do that, we actually get the transpose of this original P matrix. We get the transpose here. You can see that the 2/3 that used to be here is now in the second row, and the 2/3 that used to be here in the bottom row is now up here in the top row. And so we actually did get the transpose. Okay, so let's do this. So we're going to take P transpose, and if you want, you can put it in parentheses, doesn't really matter. And then we're going to multiply it times u0. Okay. And sure enough, it gave us the answer we expected, which was our u is equal to 1/3, 2/3, and 0. So now I want to kind of give an explanation of u2. Okay. So I said u2, we can calculate it just by taking P transpose and multiplying it times our state vector at time step 1. Okay. Now, this value here, or this vector here, again, is 1/3, 2/3, and 0. So a little trick that we can play to sort of understand a little bit better what's going on is we can say, well, how does the probability of everything that's in state 1 get moved around? How does the probability of everything that's in state 2 get moved around? And how does the probability of everything in state 0 get moved around? So one way you can kind of think about it is we actually have 3 vectors. So 1/3, 0, 0, plus 0, 2/3, 0, plus 0, 0, 0. Okay? And the reason why I'm doing this, and the whole point of it, was to isolate the probability in each one of the states. Okay? And so now this problem looks exactly like it did before, where we just had 1 being the total probability in one of the states. So what we can see here is, how does the probability that was associated with state 1 get moved around? How does the probability that was in state 2 get moved around? And how does there's no probability in state 3, how does that get moved around? And so we can sort of do that by saying, well, let's multiply P prime, and we can actually do this in line here. We're going to multiply it times the vector 1/3, 0, 0. All right? And so that returns, so if I do this multiplication first, I think that's 1/9, 2/9, and 0. Okay. And now I'm going to multiply P transpose times the second vector. Oops. Writing that in the wrong place. All right, so let's do that. So now I'm going to say P transpose times 0, 2 divided by 3, 0. Okay, and this tells us how that 2/3 of probability, how it gets moved around. And in fact, If you add these two numbers up, they should add up to 2/3. Right. So what is that? 2/9 and 4/9? Is that what that is? Maybe I'm doing my math wrong. Let's see. Yeah, 4/9. Okay. All right. And of course, if we take P transpose and we multiply it times this vector, we just get 0, 0, 0. Okay. Now, we can add this stuff all back up together, and we end up with 1/9, 4/9, and 4/9. Okay. So that was a lot of work for something we could have actually just done in one step. So again, before we said P prime times U0, that gives us U1. So I'm going to say U1 is equal to P prime times U0. We can repeat that equation by saying U2 is equal to P prime times U1. Right? And sure enough, we get the values that we expected. Right? We get the 1/9, 4/9, and 4/9. Right? And so the reason why I showed this work here is I wanted to demonstrate to you that the equation U of n plus 1 is equal to P transpose times U of n, how it kind of works. Again, all it's doing is it's saying, well, we have some probability in a state. How does that probability get moved around? And we can look at it from each of the individual states. I know. All right. Okay. So, but that wasn't really where we wanted to go, because I said, well, what's the point of doing this a whole bunch of times? What if I wanted to calculate U of 1,000? I'm not going to do this multiplication 1,000 times, right? I'm not going to calculate U of 1, U of 2, U of 3, U of 4, U of 5, all the way to U of 999, just so I could finally calculate U of 1,000. All right, there has to be a shortcut. And sure enough, the shortcut, so we can use induction, which we sort of did, is we said that U of n is equal to P of n transpose times the initial distribution that we started off with. All right. So again, let's sort of look back at this problem. So let's say we started off in state 1. All right. And I want to know, where am I in 10 time steps? Okay. So I'm going to take P to the 10th power, then multiply times the transpose, and take U of 0. All right. So let's see how we can do this in MATLAB. So we still have our P vector, or matrix. We can take it to the 10th power. And keep in mind, when you're doing a matrix to the 10th power, what you're saying is so P to the 10th is actually equal to P times P times P times P 10 times. All right? This is a matrix multiplication. You're not multiplying the first element of P, or, this is not equal to, let's say, P11 to the 10, P12 to the 10, P13 to the 10. No, that's not what's going on here. So don't do that. Just make sure you don't make that mistake. You're doing a matrix multiplication where you take P up to the 10. All right. So we can take P up to the 10th. We'll then transpose it, and we're going to multiply it times U0. Okay. And what I'm telling you is this is actually equal to U10. Okay. So if we go ahead and do that, and I'm going to just write down the numerical values. Okay, so we get 0.33, and there's probably some rounding that's going on here, so just be aware of that. Right? So this is u to the 10. And just to prove to you that that gives us the same answer as saying u to the 10 is equal to p transpose times u to the 9, where u to the 9 is equal to p transpose times u to the 8, and so forth, I'm actually going to work it out here. Okay, so I think we calculated u2. So let's do u3 equals p transpose times u2. All right, and now we can say, I'm just going to change this to u4 and u3, u5 and u4, u6 and u5, u7 and u6, 8 and 7, 9 and 8, and finally we're going to get u10 from u9. And sure enough, we end up getting the exact same values. Okay, so this becomes really helpful because there will be problems where we start saying, well, what's u to the 1000? Okay, given some initial starting condition. And so all we have to do is take p to the 1000th power. Now, you might go, or at least wonder, well, what if p gets really big? Well, p won't get really big. Okay, so let's look at what happens if we take it to the 1000th power. You can see the values across the rows still add up to 1. Okay, and this is going to be a property of our transition matrices, that even if we take them up to a very large power, they don't get bigger or smaller. So we don't start seeing really large numbers in the elements of the matrix, the resulting matrix. And so this becomes very helpful because we can say, well, if I want the u1000, right, that's just p to the 1000th power transposed times u0, right? That will be 1/3, 1/3, 1/3. Okay. Now, another good question is, well, what if we didn't start? So here we assumed we started in the first state. What if that's not where we started? So in fact, we could maybe say, well, what if u0 was 0, 1, 0? Okay. What would u10 be? And so we can go ahead and calculate that. So I'm going to reassign u0. I'm going to say u0 is equal to 0, 1, 0. Oops. And now I'm going to say u10 is equal to p up 10 transpose times u0. All right. So now we get 0.33471, 0.33059, and 0.33471. Okay? And we can compare this, actually, so let's do a quick comparison. Oops, is there a way to zoom out? Okay. So I know it might be a little bit hard to see, but we can compare the values here with the values, the values here. So this was the case where u0 started at 1, 0, 0, right? And here, this is the case where u0 started at 0, 1, 0. And you can see they're actually, the distribution after 10 steps are different, right? So this vector is different than the vector we calculated there. And it kind of makes sense, right? So think about it this way. Let's say I start my night at sound bar, okay? Where I end up at the end of the night might be completely different than if you started your night at a bar in Winter Park, right? And so it's that same idea, right? Where you start sort of determines where you end up in the future, and more generally, the probability distribution. Okay, so this is an example of how we can calculate our n-step transition probability matrix. Okay, and in fact, that's what this matrix represents. Okay, so what we're actually doing here when we say u to the n is equal to the p to the nth power transpose times u0, this matrix here, before we take the transpose, p to the n, right, it actually contains, so let's actually do it. So p to the n is going to be a matrix, okay? And let's say I take some arbitrary ij within that p to the n. So I'm picking one of the values, okay, defined by the ith row and jth column. Well, pij to the n, this is equal to the probability that at time step n, you're at state j, given that at time step 0, you started at state I. Okay? So that's the neat part about this matrix, and that's why we call it the n-step transition matrix. All right? And this is in contrast to just P. So again, this is P to the n. It's called the n-step transition matrix. Well, the transition matrix or we could say the single step is just P. Okay. So hopefully you guys found that informative, and cool.